In any case, what appeared at first very basic, before long turned out to be more confounded. Immediately following the publication of the Schwarzschild solution, two problem areas were discovered. At the focal point of the mass, at or approaches zero, this term is separated by nothing, so it explodes to boundlessness, and hence this condition separates and it can never again portray what's genuinely occurring. This known as a peculiarity. Because it is in the middle of the mass, that point might be excused, but there is also a problem spot outside of it at a special distance from the center called the Schwarzschild radius. This term explodes. So there is a subsequent peculiarity. What is happening here? The escape velocity, or the speed at which anything would need to leave the Schwarzschild radius, is the speed of light because the spacetime curvature becomes so steep at the Schwarzschild radius that nothing, not even light, would be able to escape there. Nothing ever enters a black hole. Bell dings. Imagine entangling your foe in a rocket ship and propelling him toward one. He shakes his fist consistently in response to your gaze. As he zooms in, gravity gets more grounded, so you would anticipate that he should accelerate. However, that isn't the very thing that you see. The rocket ship, on the other hand, appears to be slowing down. In addition, he appears to be shaking his fist more and more slowly. This is due to the fact that, from your point of view, he and his rocket ship do not vanish, rather, they appear to stop frozen in time at the exact moment when he should cross the event horizon, the point beyond which not even light can escape. The spaceship's light gets redder and less visible until it disappears completely. This is the manner by which any item would look crossing the occasion skyline. Light is as yet coming from where he crossed, it's simply too redshifted to see, yet in the event that you could see that light, then in principle you would see all that has at any point fallen into the dark opening frozen in its sights, including the star that framed it. However, practically speaking, photons are discharged at prudent stretches, so there will be a last photon transmitted external the skyline, and thusly these pictures will blur after some time. This is only one of the bizarre outcomes that comes out of the overall hypothesis of relativity, our ongoing best hypothesis of gravity. Both white holes and black holes were predicted by the initial solution to Einstein's equations. It likewise inferred the presence of equal universes and, surprisingly, conceivably a method for going between them. This video explains the real science behind black holes, white holes, and wormholes. A fundamental flaw in Newtonian gravity led to the development of the general theory of relativity, at least in part. In the 1600s, Isaac Newton thought about how an apple falls to the ground, the moon's orbit around the Earth, and the Earth's orbit around the sun. He came to the conclusion that anything with mass must attract other things, but his own theory made him nervous. How could masses that are so far apart exert a force on one another? He stated that one body might follow up on one more a good ways off through a vacuum without the intercession of whatever else is to me, so extraordinary in silliness that I accept no man who has an able personnel of reasoning might at any point fall into it. Exclusive who most certainly had a skillful workforce of reasoning was Albert Einstein, and more than 200 years after the fact, he sorted out how gravity is interceded. Bodies don't apply powers on one another straightforwardly. Instead, the spacetime in its immediate vicinity is curved by a mass like the Sun. This, then, at that point, bends the spacetime around it, etc. the whole way to the Earth. So the Earth circles the Sun, in light of the fact that the spacetime Earth is going through is bended. Because masses are affected by the local curvature of spacetime, there is no need to act far away. Numerically, this is depicted by Einstein's field conditions. Can you write down the Einstein field equation? This was the product of a decade of hard work by Einstein following the discovery of special relativity. On one side, the field equations basically say, tell me about the distribution of matter and energy. The opposite side lets you know what the resultant curve of spacetime is from that conveyance of issue and energy, and it's a solitary line. It appears to be a straightforward equation, doesn't it? In any case, it's not exactly one condition. It's a group of conditions, and to make life more troublesome, they're coupled conditions, so they rely on one another, and they are differential conditions, so it truly intends that there are integrals that must be finished, duh. So there's an entire bundle of steps that you want to do to tackle the field conditions. To see what an answer for these situations would seem to be, we really want a device to comprehend spacetime. So envision you're drifting around in void space. A glimmer of light goes off over your head and fans out every which way. Presently your whole future, whatever can and will at any point happen to you, will happen inside this air pocket on the grounds that the best way to receive in return is travel quicker than light. In two aspects, this air pocket is only a developing circle. In the event that we permit time to run up the screen and take depictions at customary stretches, then this light air pocket follows out a cone, your future light cone. By show, the tomahawks are scaled so that light beams generally travel at 45 degrees.